Before we begin Chapter 4, let us remember the road so far. Chapter 1 gave us the map of calculus. Chapter 2 introduced functions, input, rule, and output. Chapter 3 taught domain and range, where inputs are allowed and where outputs can go. Now the next question is natural. Once a function has a graph, how does that graph move, stretch, flip, and change shape? Here is the big question. Can you sketch a new graph in seconds if you know the parent shape? That is the power of transformations. We start with a parent graph. Then we apply simple changes, shift, stretch, compress, or reflect. A complicated graph becomes easier when we build it step by step. First, graphs have families. A linear graph has a straight line shape. A quadratic graph has a U shape. A cubic graph has an S-like shape. Pause and ask, which parent shape are we transforming? If you recognize the family first, half of the graph is already understood. Now focus on one parent graph. For this chapter, we will often use the quadratic parent graph, f of x equals x squared. But the idea works for linear, cubic, absolute value, square root, and many other graphs. The parent graph is the original shape. Every transformation should be compared with this starting shape. The first transformation is a vertical shift. Ask, what happens if every output increases? If we add a number outside the function, the graph moves up. For example, f of x plus 2 means every y value becomes 2 units larger. The x values stay in the same place. Only the outputs move upward. Now comes the transformation that confuses many students. Horizontal shifts happen inside the input. Look carefully and ask, why does x minus 2 move the graph right? The input is being changed before the rule acts, so the graph moves right to keep the same output pattern. A graph can also stretch or compress. If we multiply the whole function by 2, every output becomes twice as large. The graph becomes taller and steeper. If we multiply the function by 1/2, the outputs become smaller. The graph becomes flatter. Stretching is about changing steepness, not just changing position. A negative sign can reflect a graph. When the output becomes negative, the graph flips. Points that were above can move below. Points that were below can move above. Reflection is not a shift. It is a flip of the graph's shape across an axis. Transformations can be combined. Do not try to memorize the final picture immediately. Start with the parent graph, then shift right, then shift up, then stretch, one change at a time. This method lets you build graphs instead of guessing them. There are common mistakes. First, f of x plus 2 moves the graph up, not right. Second, f of x minus 2 moves the graph right, not left. Third, stretching changes steepness, not just position. Remember the simple rule. Outside affects vertical behavior, inside affects horizontal behavior, and a negative sign can create reflection. Chapter 4 teaches us how graphs change. Parent graphs give starting shapes. Vertical shifts move up or down. Horizontal shifts move left or right. Stretching changes steepness. Reflection flips the graph. Now we are ready for the next question. If a function changes from one point to another, how much did it change? That leads us to Chapter 5, Average Rate of Change.